Good evening, friends. So today we are continuing the laminar flow through circular pipe. So we are in the previous class we have taken the Hagen-Poiseuille equation. To arrive at the Hagen-Poiseuille equation, we need four equations. One is the velocity equation, then the shear stress equation, and then we have to take the ratio of maximum velocity to average velocity. So that is listed here, and the drop of pressure for the given length. So considering all these four equations together, finally Hagen-Poiseuille equation is arrived. Now taking the ratio of maximum velocity to average velocity. So we have the velocity equation here. So that is minus 1 by 4 mu of del P by del X into capital R square minus small r square. So here the velocity is maximum when small r is equal to 0. That is, in the pipe having the radius capital R, and when we take exactly the neutral axis of the pipe, that is exactly at the center of the pipe, so the flow is taking place at a maximum velocity. So that's why we say that the velocity is maximum when small r is equal to 0. That is exactly at the neutral axis of the pipe. So my velocity is maximum. As you move away from the axis, and if I reach the wall of the pipe, there the velocity becomes 0. So that is what we have said here. When small r is equal to capital R, my velocity will be equal to 0. That is exactly at the wall of the pipe. So the velocity is 0. Exactly at the center of the pipe. So the velocity is maximum. So we say that the velocity is maximum when small r is equal to 0. So we are substituting that in this equation, velocity. So u max is equal to minus 1 by 4 mu into del P by del X of capital R square, and this small r I am taking it as 0. So the average velocity u bar is obtained by dividing the discharge of the fluid across the section by the area of the pipe. So we know the discharge equation Q is equal to AV. So Q is equal to AV. So we are getting the velocity by dividing the discharge of the fluid Q by the cross-sectional area of the pipe. So that is A, which is pi r square. Now consider a flow through circular ring element of radius small r and the thickness dr. So that is we have shown here. So this is the pipe of radius capital R. In that pipe of radius capital R, I am taking a small elementary ring of radius small r and the thickness dr. Now I am considering the flow through this elementary ring. Now the fluid flowing per second through this elementary ring dq is equal to velocity at the radius small r into area of the ring element. So that is taking the equation Q is equal to AV. So this equation Q, so that is obtained by integrating this flow through the elementary ring. So here I am writing the expression for the flow through the elementary ring. So that is dq. Integrating this dq, I am getting the entire discharge through the pipe of radius capital R. Now dq is equal to velocity at the radius small r and into area of the ring element. Velocity at the radius small r, so that is when the flow is taking place through this elementary ring. So that velocity is considered as u into area of the ring element. So the circumference of the ring is 2 pi r into its thickness, so that is dr. Now u, we are writing it as 1 by minus 1 by 4 mu into del P by del X into capital R square minus small r square into area of the ring element. So that is 2 pi R dr. Now the total discharge in the entire pipe is integration of dq. So the integration limits are 0 to capital R. So now integration of that dq equation is written here. So in that expression, so capital R and small r are kept inside the integration and other things are taken outside the integration. So now integration of 0 from the limit 0 to capital R square minus small r square into r dr. So integrating this capital R square into r. So I am getting keeping this radius of the pipe as constant. So it is remaining r square only. So integration of r is nothing but r square by 2. Then minus of integration of r square. So that is integration of r square into r. So that is integration of r cube. It becomes r to the power of 4 by 4. So with the limits 0 to capital R. So on simplifying the discharge Q obtained is pi by 8 mu of minus del P by del X into r to the power of 4. Now average velocity U bar is equal to, okay, so Q, that is the discharge, divided by area. So Q, what we obtained is written here, and area of the pipe is pi into r square. So simplifying that average velocity, we are getting this. Now taken the ratio of maximum velocity to the average velocity. So maximum velocity is this, that we have written here, and average velocity, that also we have written here. So everything gets cancels except 8 divided by 4. So that is 2. Now it is proved that ratio of maximum velocity to average velocity is equal to 2. So in the examination also you will be asked to prove that the ratio of maximum velocity to average velocity is 2 in the case of laminar flow through the circular pipe. So for which you need to derive this part of the equation. Then the fourth equation in Hagen-Poiseuille's equation is drop of pressure over a given length of the pipe, capital L. Now I am taking the two sections 1 and 2 with the difference of L, that is the length or the distance between these two sections 1 and 2 will be capital L. The section 1 is taken at a distance of x1 from the inlet, that is the entry of the fluid into the pipe, and the section 2 is at a distance of x2 from the inlet, that is the entry of the fluid into the pipe. Now we know the average velocity, so that is 1 by 8 mu into minus del P by del X into capital R square. So just rearranging the terms, we are having this. Now integrating this, integration of minus del P by del X. So minus is taken outside, integration of dP. So we have the two sections 1 and 2. So that's what we have written here. So here also integration here. So with the limits 1 and 2. So then this dx is taken to the other side. So integration of dp is p. Substituting the integration limits, we have p1 minus p2 here. Then this ratio is taken outside the integration. So integration of dx is x with the limits 1 and 2. So it is x1 minus x2. So now taking minus outside, so here this becomes minus of this x2 minus x1. So minus and minus get cancelled on both the sides. So it is P1 minus P2 is equal to this. So P1 minus P2 is equal to, okay, so x2 minus x1. So this is x2, this is x1. So x2 minus x1 is equal to L, that is substituted here. So radius is substituted as d by 2 the whole square. So P1 minus P2 is on simplifying. So this becomes 32 mu u bar L divided by d square. So at the same time, we know that P1 minus P2 by rho g is nothing but loss of the pressure head. So divide both sides of the equation by rho g. So here we have P1 minus P2 by rho g. So here also we have 32 mu u bar L divided by rho g d square. So we know that P1 minus P2 by rho g is nothing but loss of pressure head due to friction. So that is HF. So P1 by rho g is nothing but H1, that is loss of pressure at section 1, and P2 by rho g is nothing but the loss of head at section 2. So H1 minus H2 is equal to HF. So that HF is nothing but 32 mu u bar L divided by rho g d square. So this P1 minus P2 by rho g is equal to 32 mu u bar L by rho g d square is nothing but my Hagen-Poiseuille equation. Thank you.